Title Memory Fabric Friction as a Natural Explanation for Observed Cosmic Acceleration, a Redshift Modeling Analysis in the Millar Cosmological Model. Author Lloyd Thomas Millar, Sudbury, Ontario, Canada. Abstract. Cosmic redshift has traditionally been explained by the expanding universe model, with unexpected acceleration attributed to dark energy. Here, we present an alternative explanation rooted in the Millar Cosmological Model, which introduces memory fabric friction, a natural tension effect experienced by photons traveling through the universe. Using data from Type 1a supernova, we compare the standard expansion model with two friction-based extensions, a linear model and a bell curve model. Both increase predicted redshift in line with observations, with the bell curve model providing the best fit to the rise and tapering seen in deep sky surveys. This suggests that cosmic redshift results not only from expansion, but also from measurable frictional interactions with the memory fabric. This model offers a testable, physically grounded alternative to dark energy, inviting further study and observational validation. Introduction. The late 20th century marked a turning point in cosmology. Observations of distant Type 1a supernovae revealed that the universe was not just expanding, but accelerating in its expansion. This discovery, awarded the Nobel Prize in Physics in 2011, led to the proposal of dark energy, an unknown force thought to drive this acceleration. However, dark energy remains entirely theoretical. Despite its mathematical fit to observational data, it has never been directly detected or physically explained. This opens the door to alternative interpretations. The Millar Cosmological Model, MCM, offers such an alternative. It proposes that photons experience cumulative tension as they travel through an expanding universe, a phenomenon we describe as memory fabric friction. This effect amplifies redshift without requiring dark energy, providing a physically grounded, testable explanation for the observed acceleration. Background. The discovery of cosmic acceleration came as a surprise. Based on Einstein's general relativity, scientists expected gravity to slow the expansion of the universe over time. Instead, observations of distant Type 1a supernovae showed that these objects were fainter and more redshifted than expected. Two major research teams, the Supernova Cosmology Project and the High Z Supernova Search Team, independently confirmed these results in the late 1990s. To explain this, cosmologists introduced dark energy, represented mathematically as the cosmological constant Keil in the LCDM model. Dark energy is believed to make up nearly 70% of the total energy content of the universe, driving its accelerated expansion. Yet, despite its widespread acceptance, dark energy's physical nature remains one of the greatest mysteries in modern physics. The Millar Cosmological Model takes a different approach. Rather than adding an unknown energy field, it suggests that the structure of space itself, what we call the memory fabric, plays an active role in shaping photon energy over cosmic distances. This interaction, described as frictional tension, could account for the observed redshift patterns without requiring dark energy. Theoretical framework. In the Millar Cosmological Model MCM, space is not empty. It is structured by a dynamic medium called the memory fabric, a tensioned field that carries the history of every quantum event. As photons travel through this evolving fabric, they interact with it, experiencing a cumulative friction-like tension. This interaction adds a second component to redshift beyond simple expansion. We define the total redshift as Z total equals Z expansion plus Z friction, where minus Z expansion follows Hubble's law, Z expansion H sharo D by C, with H sharo as the Hubble constant, D as distance, and C as the speed of light. Z friction represents the memory fabric friction, modeled as a function of distance and cosmic structure. We propose two friction models. One, linear friction model. Friction increases proportionally with distance, adding a small, constant tension term to redshift. Two, bell curve friction model. Friction builds up mid-journey through stretched space and then tapers off as photons approach less expanded regions near their destination. Both models predict higher redshifts than expansion alone. The bell curve model, in particular, aligns with observations showing accelerated redshift that levels off at extreme distances, something dark energy models often fail to explain without additional tuning. Methods to evaluate the predictive strength of the Millar Cosmological Model. we conducted a comparative numerical analysis using publicly available Type 1a supernova data as our observational benchmark. First, we calculated standard cosmological redshift using Hubble's law. Z expansion equals h share d by c, where minus h share is set at 70 kilometers per second per megaparsec. D is distance in megaparsecs, c is the speed of light in kilometers per second. Next, we extended this model by introducing two friction-based adjustments. 1. Linear friction model. A constant friction coefficient multiplied by distance, z friction equals μ d. 2. Bell curve friction model. A Gaussian-shaped resistance profile based on distance from the midpoint of the photon's journey. Z friction equals A at x p minus d as d0 2 as 4, where A is the peak friction amplitude, d0 is the distance midpoint, 7 is the spread of the curve. We ran these models across distances ranging from 100 to over 9,000 megaparsecs. Results were tabulated and plotted against known supernova redshifts from the Dark Energy Survey, which includes observations up to ZZ 1.13. Results. Our calculations produced clear, interpretable outcomes for both friction-based models when compared to the standard expansion model. The standard expansion model aligned well with observed redshifts at low to intermediate distances, but increasingly underestimated redshifts at larger scales, especially beyond Z 0.7, consistent with past studies that introduced dark energy to account for this gap. The linear friction model showed a steady amplification of predicted redshifts across all distances. While this brought predictions closer to observed values, it tended to overpredict at extreme distances, suggesting a constant friction model may oversimplify the behavior of cosmic structures. The bell curve friction model produced the closest match to the observed data. It accurately captured the rise and tapering of redshift amplification seen in distant supernova. The model's peak aligned with the mid-range distances where acceleration is most pronounced, and its tapering reflected the flattening trend in high redshift observations. These findings suggest that both friction effects, when applied alongside expansion, improve alignment with real-world data. However, the bell curve profile appears to best reflect the complex behavior of cosmic redshift without invoking an unobserved dark energy component. Discussion. Our results provide strong evidence that memory fabric friction could explain the observed acceleration of cosmic redshift without requiring dark energy. Both the linear and bell curve friction models improved the predictive fit to Type 1a supernova data, with the bell curve model providing the closest alignment. This outcome carries several key implications. 1. Reframing cosmic expansion redshift may not arise purely from expanding space, but also from the cumulative tension experienced by photons as they traverse the universe's large-scale structure. This tension builds as they move through denser or more stretched regions of the memory fabric and eases as they approach less expanded areas near observers. 2. Challenging the dark energy paradigm. If friction-induced tension explains the same observational patterns traditionally attributed to dark energy, this undermines the need for an unknown energy field that has never been directly observed or measured. 3. Testable predictions. The MCM makes falsifiable predictions. For example, higher redshifts should correlate with light passing through denser structures like galaxy clusters. Lower redshifts should appear when light passes through cosmic voids. Lensed light paths should show slightly greater redshift compared to direct paths at the same distance. 4. Compatibility with existing physics. The memory fabric friction effect does not require new particles, forces, or violations of general relativity. It builds on existing principles by adding a structural interaction term that has previously gone unrecognized. These findings open the door for new observational campaigns and theoretical work aimed at validating or refining this friction-based framework. They suggest that what we have long interpreted as acceleration may actually be a structural memory effect encoded in the universe itself. Conclusion. This study introduces memory fabric friction as a natural, physically grounded mechanism that amplifies cosmic redshift alongside expansion. By applying both linear and bell curve friction models to established supernova data, we demonstrate that this approach can replicate the observed acceleration without relying on the unproven concept of dark energy. The bell curve model, in particular, offers a compelling fit to the rise and tapering of redshift observed in deep sky surveys, aligning with the structural patterns of the universe's large-scale distribution of matter. This suggests that the structure of space itself, rather than a mysterious energy field, may be responsible for the extra redshift seen in distant galaxies. Our findings propose a new framework for interpreting cosmic observations, one that honors established physics while opening fresh avenues for experimental and observational testing. By reframing redshift as a combined effect of expansion and memory tension, the Millar Cosmological Model challenges the need for dark energy and invites the scientific community to test its predictions. We believe this represents a promising step forward in understanding the true nature of our universe. The author wishes to acknowledge the countless contributions of the global scientific community whose work in cosmology, astrophysics, and theoretical physics laid the foundation for this study. Special recognition goes to the teams behind the Dark Energy Survey, the Planck mission, and the many ground-based observatories whose data made this analysis possible. The author also extends personal gratitude to the independent thinkers, educators, and colleagues who inspired the pursuit of this work. Finally, this paper is dedicated to all those who have struggled through darkness, proving that the search for truth is as much a human journey as it is a scientific one. References 1 Rees A.G. et al., 1998. Observational evidence from supernovae for an accelerating universe and a cosmological constant. The Astronomical Journal, 116.3, 1009 and 38. Perlmutter S. et al., 1999. Measurements of omega and lambda from 42 high redshift supernovae. The Astrophysical Journal, 572, 565-586. 3 Planck Collaboration, 2020. Planck 2018 results. 6. Cosmological parameters. Astronomy and Astrophysics 641A6. 4. Dark Energy Survey Collaboration. 2021. Dark Energy Survey Year 3 results. Cosmological constraints from galaxy clustering and weak lensing. Data accessed at http://darkenergysurvey.org. 5. Eller 2025. The Gravity Beyond, a Unified Cosmological Framework. Unpublished manuscript, Sudbury, Ontario, Canada. In public summary. For decades, scientists have believed the universe's expansion is accelerating because of a mysterious force called dark energy. But despite years of searching, dark energy has never been seen or measured. In this paper, I propose a different idea called memory fabric friction. It suggests that light from distant galaxies doesn't just stretch as the universe expands, it also drags against the fabric of space itself, building up tiny amounts of tension along the way. When we apply this idea to real astronomical data, it matches what we actually observe, without needing dark energy at all. This means the universe's structure, not some unknown force, might explain why distant galaxies appear to speed away faster than expected. We invite researchers and curious minds everywhere to join us in testing this idea and exploring what it might reveal about the true nature of our universe.